continue from yesterday's lecture. So please go ahead.
Okay, yeah, thanks a lot. I had to stop a little bit in the middle of something, but anyway, let me recall very briefly some of the key things that you should remember for today from yesterday's talk. So I started by an introduction to this classical problem to describe isomonodromic deformations. And what this leads to is the all-important notion of a tau function, which is defined by this equation in terms of the solution to the equations describing an isomonodromic flow. And what was emphasized was that, the traditional definition, it doesn't fix the dependence of this function on the monodromy data. And there are various reasons which may motivate one to look for a natural definition of which would fix this dependence. And then this led us to discuss how to parameterize monodromy data in general. So I sketched very briefly, the description, the definition of the character variety, its algebraic and Poisson structure, and sort of the most important types of coordinates that are relevant in this context, which are the Fock-Gontrov coordinates or coordinates of Fenchel-Nielsen type. All right, so I shall not repeat this. I will also summarize sort of the main proposal for how to fix it in a different way a little later. What I now want to start with is a discussion of how exact WKB helps to define particularly natural coordinates and how to basically cover the space of parameters of these differential equations whose monodromy we're deforming by, say, local coordinates, which are in a certain sense canonical, because somehow the exact WKB gives a natural choice for all the data determining such coordinates. So that is what I want to start with, but yes, I should apologize. The discussion has to be extremely brief and sketchy in various ways, so I just want to give you sort of the flavor of how that works. So the point is, okay, our differential operator that we're interested in, it took this form. So there's just the second derivative. We decorate it in order to have a useful expansion parameter that now becomes sort of the key player with this factor h bar, as is sort of familiar from quantum mechanics, where this would be the Schrödinger operators. And then there is what in quantum mechanics we would call the potential. Here it's a meromorphic function on the four-punctured sphere, because we allow it to have, in our context, apparent singularities. That may be an issue, by the way, for some of the following statements here. So there is, it would be, what is by now very well investigated, and in the audience, Nikita Nikolaev has recently made important contributions to this, is the exact WKB expansion of the solutions to these equations when there are no apparent singularities. So when this here is holomorphic in the domain of definition of our interest, I think it would be interesting, and I expect that sort of most of what I want to say generalizes to the case where there are apparent singularities, but to the best of my knowledge, maybe Nikita can comment, this hasn't been done yet. So this is sort of, the extension to the case with apparent singularities is in this sense a conjecture that would be important to settle to put the following propositions or proposals on firm mathematical ground. Okay, but in any case, how does it work? There is, of course, no problem to begin with to do the following game, which is sort of the standard game of WKB analysis. You make an ansatz for the solution to this differential equation of the following form. So you represent it as exponential of some integral over a function s odd here, which is then defined from the solution to the Riccati equation, which is basically taking here the potential QH bar, which appears in the differential equation, as the input data, and the output here of the solution to this equation would be then the unknown function S, for which there is a recursive series expansion determined from basically the lowest piece. And for the lowest piece, we have a sign choice to make. The lowest piece is the one with the index k equals to -1. So there are two possible choices for the lowest piece. And we're taking here an odd linear combination of the two possible choices corresponding to the two ways of taking the square root here. Okay, so this defines a formal series, right? You just, it's basically a straightforward exercise that you plug in an ansatz of this form, like written here in equation number 9, into this equation, which is here, the Riccati equation. Well, I'm sure, well, Nikita probably has explained it better than I can do it here. Yeah, so then you will find that to lowest order you have this condition, and then the higher coefficients, the higher expansion coefficients here are uniquely determined until in terms of the lower ones through this equation. So that's a relatively straightforward part. What is not so straightforward is the Borel summability of this series, but in some cases, the results to this effect, which are relevant here, are generically attributed to Koike and Schäfke, and the manuscript was not available, at least to me, where this was done, and so it is very good that now Nikita Nikolaev has presented proofs of relevant results in these two papers. So what is being proved there in particular is that the so-called Wörth symbols, which is basically what appears here as the integrand of the solution of this formula for the solution to the equation defined by the potential QH bar, so that this object, which is a priori just a formal series in powers of H bar, that it can be Borel summable if the argument stays well away from the so-called Stokes lines. And this is sort of the important thing I need to introduce. Namely, you can just plot on the Riemann surface that we're working on the trajectories, which are defined by this condition here. So we're taking possibly here rotated with a adjustable parameter lambda, whose argument we're taking. Oh, actually, I see another typo to be corrected. So the lambda should be H bar. So this is then what is relevant for this equation. Lambda should be replaced by H bar here. Yeah, and then, well, we're taking the lines where this function W, which basically can be taken as a new coordinate on the Riemann surface, which is defined through this potential Q being here the lowest order part of this expansion, so which is here denoted Q0. And yeah, this defines a new coordinate on our Riemann surface. Yeah, and so we're plotting the lines of a constant imaginary part. This gives us some graph on the surface that we're working on. So here are some pictures of how it can look like in various cases. For a case where we're looking at least at a part of the Riemann surface containing two of the punctures, so the mark points that we've taken out. So it's perhaps a little small here, but there are some black dots here in these in the corners of this diagram, like here and there. Then there are the orange little crosses, which are branch points of this covering that is defined by the quadratic differential. I mean, this is something that we've seen in this conference already a couple of times. this is the same as what is called a spectral network. So it was in some way, of course, in Andy's talk and in Fei Yan's talk. And so that is the same thing here, specialized to the case at hand. And here we're just sort of, for the sake of illustration, drawing a couple of pictures for, well, a part of this network where we just have two punctures well separated from the rest. And there we can have, in general, two types. I mean, the point I want to make is that there is a partial classification that you can do of the types of graph, which of course will depend here on the choice of Q. And the choice of Q was the choice of these, well, leading order, so, or the Q0, so what we get when setting here H bar to 0 in the potential. So this determines this graph through the formula here. And yeah, we have different types to be considered. Some have a structure like here, where we sort of always emanate from a branch point and fall into a puncture. Good, one can easily convince oneself that around a puncture of the regular type we're considering here, we always have three such lines, Stokes lines emerging. Here are other possibilities for how it can look like when we vary the parameters in the potential. So then, so here is a puncture, and there's a puncture, and it falls sort of somewhat differently from the branch points into the punctures. So these are actually, one can classify, that was classified by Aoki and collaborators in this situation, that you have basically a three punctured sphere separated from the rest sufficiently far. Then these are the possibilities that you can have in the vicinity of, say, two punctures separated from the rest. But what is interesting is, of course, the other possibility. So yeah, what you can also notice is that these Stokes graphs, they always define a triangulation, basically by connecting the punctures in such a way that you do not cross here any Stokes line. So that defines, so any such graph of this type defines a triangulation of the Riemann surface. And what we're going to argue is that, yeah, there are naturally associated coordinates to this, which are then Fock-Gontrov coordinates. Therefore, these graphs will be called FG type Stokes graphs. Then there are others where we have basically what is called ring domains, namely there basically we form cycles where, in particular, for example, like here from a branch point, we go back to a branch point, and likewise here, and so on. And well, if again, you keep in mind, this is a picture where sort of you think out here, there's the rest of the Riemann surface, then there's in particular closed lines that you can draw to separate this pair of punctures from the rest. So this defines naturally cycles on the Riemann surface, and these cycles naturally define a Pans decomposition. So these types of graphs naturally define Pans decompositions, and no wonder we will claim they will be related to Fenchel-Nielsen type coordinates, which are also naturally associated with Pans decompositions. All right, yeah, as well, again, I want to apologize that I have to be so extremely brief and sketchy here. A key player then are these Worosz symbols, which are these integrals over S odd along cycles on the cover, which is defined, I mean, on which this square root of Q is defined. Okay, so that is the spectral curve that in Andy's talk has figured prominently. So on that, so we consider cycles better on that spectral curve, on that cover. And we take them to integrate here these S odd, which is this key player in the reconstruction of solutions through Borel summation. And so this gives us, for any choice of a cycle, a complex number. And the complex number is, of course, a function of all the parameters we have in QH bar. So therefore, it is becoming a function on the space of parameters of which are in our potential. and these contain in particular the dynamical variables of the isomonodromic flows after all. Okay, so in the case where this guy has no apparent singularities, which for us, however, are important as stressed, there are results conjectured by Tom Bridgeland and then by now rigorously proven by Dylan Allegretti, that these Vorosh symbols can be identified with the Fock-Gontrov coordinates in such cases as discussed here. And these are, after all, the solutions of what has been discussed at this conference already, in Andy's talk in particular. They solve a Riemann-Hilbert type problem defined by, well, the Donaldson-Thomas invariants that you can associate to certain local Calabi-Yaos as were introduced also in Andy's talk. We will come back to this at least briefly a little later. But in any case, well, when you have these Donaldson-Thomas invariants, it has been discussed in Andy's talk that they define a certain Riemann-Hilbert type problem. And these results of Tom and Dylan then give this identification between the Vorosh symbols and the Fock-Gontrov coordinates, which solve this Riemann-Hilbert type problem. Here it is sort of written out on the slide that for the story that I'm putting forward here, that I would like to propose, a generalization needs to be worked out for the case where there are apparent singularities. And what I also want to mention, I mean, also this is in some sense not fully finished business, but we can say something. The question is, what is the relation between, say, the networks of this Fenchel-Nielsen type and coordinates defined through exact WKB? There is work in the literature. Lotte and collaborators have worked on this. There are some results that we have used in our work by Iwaki et al. And Aoki et al., which in particular cover the case of the three-punctured sphere, whereas, well, in particular, the solutions to this equation here for the three-punctured sphere, they are known to be Borel summable, and there are some beautiful explicit formulae for this. And what we have done in our work to get from the three-punctured sphere to the four-punctured sphere is to consider a situation where the four-punctured sphere factorizes by well, being separated with a reasonably large cylinder into two three-punctured spheres. And then one can use the exact WKB on the three-punctured spheres to define canonical solutions on them, also for the case here where we have Stokes graphs of this type. And this can be used as the basis for a definition of Fenchel-Nielsen type coordinates. So basically, the observation that we have been exploiting to define Fenchel-Nielsen type coordinates for this case is that if you normalize your solutions to this differential equation in the three-punctured sphere, and that is possible thanks to the work mentioned, then this can be the basis of a precise definition of Fenchel-Nielsen type coordinates, because then it's just a gluing game to define the Fenchel-Nielsen type coordinates. What would be nicer, but what I'm somewhat uncertain about, is to also to generalize the description in terms of Vorosh symbols to the case of Fenchel-Nielsen networks. It could well be that in this round there are people who have understood this already, but I feel slightly uncertain about the status of this. So whether in this case of a Fenchel-Nielsen network, actually the Fenchel-Nielsen coordinates that we define by an indirect method are directly representable as Vorosh symbols. That is, to me, not 100% clear, but well, we had a workaround in terms of the factorization of C04 into three-punctured spheres, which at least leads to a definition of Fenchel-Nielsen type coordinates based on exact WKB, though somewhat more indirectly. Okay. Here is a informal summary now of basically all that has happened up to now, and the resulting picture, or the most important elements of the resulting picture, which is supposed to round off this part and well, prepare for, well, it can serve as a reminder, and it can prepare a little bit for some of the next things I want to discuss. So what we're considering one more time is the isomonodromic deformations of differential operators of this form. We can do it more generally, but say just for the sake of illustration and to keep things simple, we've picked the case of the 4-punctured sphere, and then QH bar would have a single apparent singularity at a point U on that Riemann surface. Good. What is something that I didn't stress yet, but which, no, I mean, I basically mentioned it, but maybe I didn't stress it enough. Now let's note the parameters, which are U and V, which is the position of the apparent singularity and the residue at the apparent singularity. They determine in particular here this leading piece in H bar expansion of QH bar, which is of course the same as what you get by just setting H bar equals to 0 when you think of it as a numerical parameter. Because, yeah, in Q0, what is sort of the key parameter when we keep fixed parameters at punctures, that is this H, that was the Hamiltonian generating the isomonodromic flows. This was a function of U and V. And when you know how H is determined in terms of U and V, then it basically determines the Q0. So, well, a simple observation, but important for what follows. The point then being that, of course, now, well, the Q0 was determining the Stokes graphs, right? So what we now are, the game we're now playing is our parameter space, which is the space of all the parameters here in this differential operator, we now want to decompose it into chambers, which are labeled by the types of the Stokes graphs. So types are, for example, I mean, this here are sort of the types of Stokes graphs that we can have on the 3-punctured sphere, and of course on the 4-punctured sphere you will have some more, because then you need to connect sort of these parts to the parts from another 3-punctured sphere, and you're getting thereby the different types of Stokes graph on the 3-punctured sphere. But yeah, the Stokes graph is uniquely determined by the Q0. So therefore, if we just ask what's the type of Stokes graph, then thereby we're getting a decomposition of the parameter space into chambers. So let's just label them by some index I. So we have these chambers UI, and we've broken up the parameter space that we work on into chambers, which are determined by this Q0. And this in turn is determined by, well, U and V, so the dynamical variables we're having in the isomonodromic flows. Well, then, at least once these caveats that I pointed out are removed, the exact WKB would give us coordinates for each of these chambers. So we would thereby get an atlas on our parameter space M, covered with these coordinates sigma I, eta I, which we can, with a little bit of extra work, to be made into Darboux coordinates. That is another thing that I kept a little bit under the rug. The Fock-Gontroff coordinates are not immediately Darboux coordinates by themselves, but there is a way to define Darboux coordinates from them if you accept certain choices for which, as I had mentioned, for example, Kashaev has a natural formalism to take care of them.
Sorry, excuse me, you view Z as fixed for the whole game, do you, for now?
Now I'm viewing Z as fixed for the moment, yes. So for the moment, I'm considering a fixed Z. So then, well, but of course, yes, I can fiber everything then over Z, and it would flow. It would flow, right? Okay, yeah, and the main point was that then, and this is really something I want to put an emphasis on, that we had a way then to associate to each coordinates the corresponding tau functions, and one of the most important properties of this assignment is that the assignment of the tau functions to the coordinates is such that in each of these coordinate systems we have these magic type of series expansions, which in the case that we have Fencher-Nielsen coordinates, at least, give us a representation in terms of objects which have a meaning in, well, completely different parts of mathematics, like, for example, very thorough representation theory. So, and this, I believe, really is sort of a door to some of the, a window to some of the real deep features behind, or deep aspects of mathematics behind this theory of isomonotomic tau functions. So really, this, I think, is a very important, well, feature, structural aspect, or however you may want to call it. Good, and then, yeah, then of course it's natural to ask, how do you change coordinates from patch to patch? Of course, yes, there are changes of coordinates which are just induced from a change of the chamber, which you can work out. We have given examples, say for Fock-Goncharov to Fock-Goncharov. But the point was that we claim there always exist such functions here which represent the change of normalization relating the different tau functions which are associated to the respective chambers. And yeah, we characterize these as difference generating functions. Yeah, the thing to be emphasized is that basically these are canonically associated to the changes of coordinates we're considering. So in this sense, really here, yeah, that is perhaps, at least as far as I can tell, the closest we can get to a canonical way of fixing the dependence of tau functions on monodromy data. We can't quite, I mean, due to the dependence, at least here in this game, on choices of coordinates, we can't quite hope to have just one choice which does it all over the parameter space. But upon breaking it into chambers, which is done in a way which is pretty canonical by the exact WKB, we get something which seems to be as close as it can get. So. All right, so that is the summary.
Excuse me.
Yes.
Excuse me, can I ask a question?
Sure, of course.
So for your tau function, for how h bar is included, can you explain the h bar dependence of your tau function?
Oh, the h bar dependence, yeah. Okay, that's I mean, first of all, let me stress, it's of course just suppressed in the notations. It is always there, right? It is always here, parametrically there. And the way it is determined is, of course, through the definition of the coordinates in terms of exact WKB, right? We view the sigma and eta as functions on the parameter space, but the relationship is based on the construction of the Walsh symbol, so it will always involve the parameter h bar in a very important way. And okay, as you're asking, I think I see where your question is going, and it would be very interesting sort of to relate this to your work, where you have done something certainly related for the Pont-Levis 1 case, right? So, and what I'm kind of suggesting are some elements which would be generalizations or elements of the generalization of this story to the Pont-Levis 6 case. And one, I mean, okay, let me take the chance just to make the following remark. It would be great, and I would hope that, say, for example, topological recursion could be taken as the definition for this tau function. So the dream would be that ultimately, for example, topological recursion could be summable. Here, what we do is a kind of workaround. We are sort of shifting everything into the coordinates. And then from the coordinates, once the coordinates are defined, for which to a large extent, I believe we can just rely on the exact WKB, then in some sense, let me go to the right place. You see, you would, so assuming you have defined eta, you can view this equation here then as a difference equation, which defines you tau in terms of eta. And that is, I think, in spirit similar to something which has appeared in your talk, where there was a similar relationship between partition functions and then this, say, what is often called magnetic coordinate. So, but yes, I mean, it's probably little farther away, sort of to really reconstruct the tau function from the topological recursion by generalizing. I mean, maybe you can do it. I would hope so very much. But here, basically, yeah, the way it goes is to define coordinates through exact WKB, and then the tau functions are associated to that more indirectly. That's the best we can do at the moment, it seems.
As far as I know, last, or maybe 2 years ago, Einar and Garcia Faraday and Marshall Orantan gave some proof in all Panve 6 equation, I think. So namely, the topological recursion can construct this kind of expansion or expression for all Panve equation, including some higher order version.
Okay, thanks for pointing this out. I would need to look at it, but did they, for example, study Stokes phenomena of the summation? That would then, of course, that should then lead exactly to these formulae here, right?
Yeah, they are not discussing some relation to this monodromy parameter.
Yeah. No, that would be the important part. Would be, yeah.
Sorry, could you repeat the reference, please?
Sorry?
Could you repeat the reference, please, that you mentioned?
Einar and Garcia Faraday wrote a paper
yes.
in 2019, and at the same day, Olivier Marshall and Nicolas Orantan wrote a similar paper. It appears on arXiv in the same day.
Thank you.
Yeah. Thanks very much for these questions and comments.
Yeah, thank you.
Okay, well, it seems I'm doing rather badly with time in my talks. Good. I want to briefly, I mean, all this was sort of just based on the classical theory of isomonodromic deformations, and then, okay, it was motivated by the problem to normalize tau functions, etc. I quickly want to point out that what in some sense for many of you will have been obvious already, that what I'm describing there is closely related to the solution of Riemann-Hilbert type problems as Gayotto, Moore, and Knightsky have proposed, and the variants thereof that were then really made mathematically precise by Tom Bridgeland and collaborators and other subsequent works. So yeah, the context in which one is working, this is basically a reminder from Andy's talk, would be local Calabi-Yaus of the so-called class sigma. This is, well, I mean, a personal suggestion for a name. It's an gauge theory related to class S, and S spectral curve is often denoted by letter sigma, so let's call them class sigma. Well, I'm not sure this is a great name, but anyway, we can adopt it. So yes, we're taking a quadratic differential on a complex surface C. This here will be then, in the concrete example, this Q0, which determines the Stokes graphs. And from that, you can define a curve in the cotangent bundle of the underlying curve, which for us is always the four-punctured sphere, as an illustrative example by setting this guy here to 0, and that is just y squared minus q of x. And then, yeah, we use the F sigma to define one equation for four complex variables, thereby defining a threefold. So that is just a reminder on what Andy has been discussing. And basically, the complex structures of such threefolds will be parametrized by the so-called period coordinates. We're taking the square root of here this potential q. And that is, of course, well defined then on this cover sigma. And we can take its periods along a canonical basis. Here are some indices I had wanted to remove. I just wanted to consider the single coordinate case. So this here, the index R would appear in the case that we have more complex structure deformations than we have in our favorite example. But in any case, the picture is very uniform. We're just taking a canonical basis for the odd homology of this spectral curve. computing the periods, and this gives the structure of special geometry to the part of the parameters which are contained in the Q, this leading part of the quadratic differential. There is, however, other parts that we don't quite see in that because they're not in the Q0, namely, for example, these residue, it appears at the order h bar in the expansion of our QH bar. So there's more parameters to be considered, but what one may observe, and here I again have to be a little brutally brief, these parameters, what they define is a priori a point in the cotangent bundle of the Riemann surface, but they do satisfy this interesting equation here. Namely, it means these parameters satisfy the equation for being on the spectral curve. And this is nothing but a restatement or a consequence of the fact that U and V are coming from an apparent singularity. And then, yeah, we can do sort of the usual game. We can, I mean, having a point on the spectral curve, we can map it with an able map to the prim of our spectral curve, and thereby introducing a complex flat coordinate for the torus representing the prim. We're getting coordinates A check, and theta for the parameter space of our interest. We can also, that is just a notational preparation for what I want to present in the following. We can split it into two real parameters. So the theta is a complex one, the image of the able map, and we split it into two real parameters by using the tau basically as a kind of replacement of imaginary unit, and the tau is the second derivative of the prepotential, which represents the integrals along the dual cycles, thanks to special geometry relations. All right, yeah, and then with this we can formulate a Riemann-Hilbert type problem, which is very similar to the one Andy has been discussing. So we can look for Dabou coordinates using here our notations that will be called sigma I eta I, where I then refers to some charts that we can use to cover the coordinates, to cover our parameter space. And one of the key points is here that the coordinates A and A check, what they describe is the divergent part in the asymptotic behavior when we send H bar to 0. So it has this leading behavior like so. And then there's a subleading bit which involves these thetas, so which we had split here in this way. So that is sort of the requirement, part of the requirement for here our the dependence of our coordinate sigma, which we now can view as functions, say, of A and the thetas when H bar goes to 0. And secondly, well, the coordinates, the changes of coordinates should have this cluster-like form determined essentially by these data omega of gamma, the DT invariant satisfying Konsevich-Sobelmann wall crossing formula. And the very formulation here, as already Andy has stressed, of course, rests on a lot of foundational work on, in particular, well, how to define these data properly of Bridge and Smith, Haydn, Konsevich, Katsakov, and Haydn, and probably this is even incomplete list. Please correct or supplement wherever necessary, in particular, about these references. All right, so this, yes, is a type of Riemann-Hilbert problem that we have heard about in this conference already a couple of times. And we can now we've now specialized it to a case at hand. And the main proposal then reformulated is that, yeah, indeed, there is a solution to this BPS Riemann-Hilbert problem, which is basically provided by exact WKB applied to these Schrödinger operators with apparent singularities, and the solution determines a natural line bundle whose transition functions are the difference generating functions for changes of coordinates. The normalized isomonodromic tau functions form a section of this line bundle, and there are essentially unique bases for the space of sections of this line bundle where we have this magic series expansion of the type that were discovered by Oleg Lisovy and his collaborators, and which have, well, subsequently gained a lot of prominence and a lot of other derivations as well as interpretations. Well, yeah, we're now at a point where you may notice there was something similar in Andy's talk, and that in a sense was, well, what perhaps one of the main points he arrived at. And some in the literature, similar line bundles have also appeared in the work of Alexandrov, Persson, Piolin, and Andy several years ago by now, on in particular hypermultiplet moduli spaces or the QK-HK correspondence. It is not yet clear in generality how these line bundles are related, but as already sort of in the discussion part of last lecture briefly indicated, I think there's good reason to believe that in fact the line bundles which appeared in our story are closely related, essentially equivalent to the line bundles that were discussed by Andy and have appeared in this previous work. The first step to be taken is a simple one. Our line bundle was using difference generating functions, which we constructed from a special function we denoted E of x, and that was essentially a ratio of Barnes gamma functions. On the other hand, in the way, for example, Andy and Boris et al., Sergei, Boris et al. Were introducing the line bundle, there was always the dialogues appearing. And of course, yeah, it's nice to see and kind of remarkable in various ways that they are closely related. So here is this Barnes thing, here's the dialogue. And really, well, that's a remarkable identity because, for example, what you may wonder is about analytic properties. Dialogue is somewhat subtle with its analytic properties. You may wonder about analytic continuation and so on. This formula makes it very transparent. Here on the left, the advantage of this guy is its meromorphic function of x. It has very simple analytic properties as function of x. So, well, this is just one point to make clear this is a magic formula, and it plays now a key role in just relating. So you can then compare, just by computations resting on this formula, our phi, that was the difference generating function. Then there is, it's an identity that it is proportional up to something that you just see as a, well, change. I mean, you can identify just with a change of trivialization of the line bundle if you're adopting this interpretation. And then the psi that you're getting after splitting of this factor has this formula, well, the log of psi has this formula. And what it is the ordinary generating function where you take derivatives instead of finite differences. And if you do not take here a factor of 2, but just 1 in front, then there is the Rogers dialog, which was the version that explicitly appeared in Andy's talk. Of course, you have to prove all this, say, for all possible flips. That will require a little bit of formalism, but yeah, I have relatively little doubt that it will work out basically completely analogously and thereby establish the equivalence of these line bundles in question. Here, I'm tempted to skip it or very briefly to summarize it to leave a little bit of time for some other bit I still want to get to. What you may ask is, of course, if the thing that we arrived at in a relatively indirect way, which was the assignment of normalized tau functions to coordinate systems, and the fact that the relation between these are representable in terms of difference generating functions, you may wonder if there's a more illuminating conceptual or simple way to see it. And that could come, but I don't claim that I understand it in full yet, but it could come from a relation which has been pointed out by Bertola and Korotkin, and in a somewhat different formulation or somewhat different framework derived by Nikita Nekrasov, between a generating function for a certain change of Darboux coordinates, which I will introduce quickly in a moment, and the tau function. The key point on which everything rests is that the monodromy map is symplectic, and it becomes particularly nice and simple using the Dabou coordinates, say in the example we have used. Namely, then it would really mean that basically the holomorphic symplectic form that you assign to our coordinates v and u, well, this is just what you get from the Poisson bracket we've been using to write down the isomonodromic flow equations. So the associated symplectic form after restricting to symplectic leaves is then just this one. And there is the natural symplectic form on the character variety, which is also just obtained from the Poisson structure I've written by restriction to symplectic leaves. And then you can take the monodromy map, which maps you from the differential operators to the character variety, and pull back these symplectic forms under it. And yes, the theorem, which has a certain history here, Hitchin, Alexeyev, Malkin, Korotkin, Samtleben, already some time ago for closed Riemann surfaces for the Schlesinger system. It appears that there's more recent work doing exactly what we need for Schlesinger. So that is Bertola Korotkin. So yeah, the monodromy map is symplectic. Let's just take it as a piece of wisdom we can use. And yeah, what this implies is that then there are generating functions for changes of coordinates obtained by picking a symplectic potential that is a one form whose exterior derivative would reproduce here the symplectic forms. So when this of course, you need to have a preference of sigma over eta or u over v. But with this, of course, yeah, I mean, just the fact that both eta and sigma and v and u, after taking the exterior derivative and, well, I'm suppressing here the pullback in notations, that they represent basically the same symplectic form. It implies that this guy here is closed, therefore it's locally exact, and so this therefore introduces the function S, which is in the sense of, say, Hamiltonian mechanics, the generating function for the change of variables, which just means that when you differentiate S with respect to sigma, it produces the conjugate variable eta. And likewise, with a minus sign, when you differentiate it with respect to u, it gives the v. That is the generating function. And what you can then do, here I'm using the formulation in the paper of Nekrasov, you can take the generating function, but yeah, you need to add some extra terms, which are, well, by taking derivatives. Here's also an important extra term with sigma eta, which I think should be compared sort of to factors like this, which we had in the comparison. And yeah, what you see is, and furthermore, I mean, what's the point here, right? You want, in the tau function, you want it to satisfy, or again, I forgot the log, you want it to satisfy this equation here when you differentiate while keeping monodromy data fixed. Here you have, however, a different type of dependencies. Monodromy data you have only here in the form of sigma. What you have to do is here to consider u as a u of the monodromy data in Z, which is obtained as the solution to this equation here, so which defines in particular the dependence with respect to eta. All right, so yeah, you have to really be careful that you differentiate here with the right variables fixed, which here, of course, are supposed to be the monodromies. So this observation by itself may already indicate that there must be something tricky in the relation between generating function and the tau function. Yeah, but this is the formula that Nekrasov writes. So there is such a relation.
Sorry, which paper of Nekrasov is this in?
It's from 2000, I think July 2020. I can dig out the reference a little later if you.
Okay, that's great. Thanks.
So, yeah.
That will be enough.
Yeah. Right. So good. So there's this relation, and of course, well, I mean, when you change, for example, here the Dabou coordinates, then generating functions do what they do. They change by ordinary generating functions for the changes of the Taboo coordinates, say, on character variety. So they would give the change of the generating functions would give things like here the psi, the ordinary generating functions. But there is this sort of correction term here involving the Taboo coordinates, and just by the observation that we have made here, it follows that with this correction, indeed, the changes of Taboo coordinates, which are represented in terms of ordinary generating functions, will then translate in terms of the tau functions into changes of coordinates of the difference type. So I think this basically follows from our observation above, and this I mean, it's an indication, and I believe this can be a first step to understanding parts of the story I'm presenting here, perhaps in a more direct, more geometric or more Poisson geometric way. But let me stress one thing, what is probably not immediate from this approach via generating function will be the analytic properties of the tau function as function of sigma and eta and so on, because these expansions here, they exhibit whenever we have them and whenever we know more about here the right-hand side, they exhibit sort of some remarkable analytic continuation, the existence of remarkable analytic continuations, which are not at all obvious from the definition via the generating functions. Okay, but with this, I really want to leave sort of this class of examples. And actually, yes, I need to stop sharing in order to go to another set of slides. Perhaps you can take the opportunity to ask questions now while I sort of open another file for a last part. So yeah, really, I'm sorry, I'm really running out of time. Are there any questions concerning this part already?
So you just wrote this formula that's from Bertola Korokin and Nekrasov, and you said that that quantity obeys the equation that the tau function is supposed to obey. But then I didn't completely get what you were saying. Are you saying that that one ought to coincide with your properly normalized tau function, or?
I think so. It must. Yeah, I think it must. Yes, and basically,
okay.
Yes. Okay. Further questions? All right. So, do you see the other slides?
Yes.
Okay, thanks. Good. So, I mean, yes, the last, I guess, 5 minutes, I very quickly want to talk about applications of all this to topological string theory and what it can have or should have to do with topological string theory. And this is in some sense the second part of my talk, which now is going to be a little brief. Anyway, let's say something. Yeah, what we can consider, and that is of course a very old subject, we can consider a B-model topological string on Calabi-Yau manifolds. And the usual worldsheet definition gives, and that is long known in general, just asymptotic series in powers of lambda, which is the topological string coupling, and the FGs in particular, for example, have a nice mathematical definition as Gromov-Witten invariants, and sometimes we can compute some generating functions and so on. There's a lot of nice work. But what is, I think, very little known about is whether there exist summations like this. So it is well known that this is a divergent series. But what you can ask is, do there exist functions having this as asymptotic expansion, which raises several other questions, functions on which space, or do you really want functions or other sections of a line bundle or what? And yeah, in particular, well, what kind of dependencies do we care about from the point of view of topological string theory? In particular, of course, it should be a function of scalar moduli, or using mirror symmetry, complex structure moduli. So this is what we refer to as the T's, Kähler coordinates on Kähler moduli space. And so the question, for example, or the dream one could have is that there exist natural geometric structures on these spaces, or maybe some enhancement thereof, which would make the Z top, or maybe some related object that could be called tau function, a local section of some natural geometric object, and where furthermore then it really has nice analytic properties as function of these parameters, as actual function, at least locally defined function of such parameters like t. So that is sort of the general motivating goal. And yeah, part of what our results here are in the work are that there are examples where this dream is reality, namely for the Calabi-Yau manifolds of the class sigma. So for some of them, there exist toric Calabi-Yaus, which, well, where the Kähler parameter in particular involve a parameter we call Q. And when you tune it to 1, so there's a deformation. So the toric Calabi-Yau is a deformation of these Calabi-Yaus of class sigma that we have been discussing and that Andy has been talking about. If this is so, we can calculate our Z top from the topological vertex. So there's a rule, you take the toric diagram, then there produces you some sums over Young diagrams, some of which you can do and so on. So for the case at hand, you can do it. You can take the limit q equals to 1, and in fact, there is a match with the z's, which appeared in the expansion of the tau function for certain Fn-type coordinates. And that is sort of really the thing that you have to be careful about, namely, what is the precise match? I mean, what precise coordinates do you have to use in order to find a match? Well, and the sort of flavor here of this game is that this is not the only toric diagram you could use to cover the Kähler moduli space of these toric Calabi-Yaus. There are similar toric diagrams related by flops. And these changes of the toric diagram, they do lead, just compute, but that was basically well known, it leads to changes, jumps of Z top. And sort of what got a good part of our story started was the observation that we can set up a nice dictionary between toric diagrams and Fenchel-Nielsen type networks in such a way that we find a precise match, namely the zi's, which are the expansion coefficients of tau functions, are exactly what we get from this calculation via topological vertex. Okay, so there it seems to work, and in particular, yeah, so I mean, the lesson there was the Z-top wants to jump, I mean, or we cannot avoid it to jump, but on the other hand, there seems to be a nice sort of geometry in which these jumps naturally appear and are naturally part of a beautiful geometric structure that governs this. And this was what all the previous part of the talk was about. Very briefly, I want to mention some new results, which then are a first step sort of towards extending this picture beyond this relatively special class sigma of Calabi-Yaus. Namely, we could look at the resolved conifold, one of the most popular and most studied toric Calabi-Yaus in this thing, which was well, used over and over again to illustrate various features, and in particular, Tom has used it as an example for his Riemann-Hilbert problem. Okay, yeah, I think I'm really running out of time. Maybe you can give me a hint of, should I take 2 or 3 more minutes to conclude, or what's sort of the timeline I should make?
Yes, sure, a few minutes, that's already fine.
A few minutes, okay, so good. Then I don't explain you what Borel summation is, which most of you will know. What we know in the case of the resolved conifold is the explicit form of the expansion here of the topological string. I mean, this one here, the FGs, they're all explicitly known. And here you see the formula for them, which are then functions of the Kähler parameter, right? So you see the resolved conifold basically as a part of our toric diagram here. And here's the toric diagram of the resolved conifold, has one Kähler parameter, or well, exponentiated Kähler parameter. And yeah, you can write sort of the whole asymptotic series in terms of this. Well, we have some results on the Borel summability of this thing. Here's the formula. So we can prove this series is Borel summable. And it is basically down to computing what is the Laplace transform of the Borel sum. So here's the formula. I should mention this uses and generalizes some ideas of Garoufalidis-Kashaev, where they did a similar exercise for the quantum dialogue. Okay, so that's what we have. And then we analyze the Stokes phenomena, the jumps of this guy. So using the Borel transform, well, we can compute it because the Borel transform has basically strings of poles which lie on these rays here. And you can have here the choice of the contour you want to use in the integration. And whenever you sort of stay in a wedge, you get nice analytic functions. But of course, you get different analytic functions for each wedge. And the jumps across the wedges, well, they're of course computable once you have here the Borel transform. And here's the formula. And here, of course, this should already ring a bell. This combination of dialogue with some logs we've seen before. But okay, we can sort of make it more beautiful. We can rewrite, for example, F0, which is the case where we integrate the Borel transform along the positive real axis. That gives us F0. And there's a nice formula that also some of you may recognize. That is what is called the triple sine function. The jumps in turn, right? The jumps were of enormous interest for us. Well, using this magic identity that I stressed already a lot, you can rewrite the exponential thereof in terms again of E. That is the E function, which is ratio of Barnes-Double gamma functions. So these are our jumps, and this guy reappears. And of course, once you know this, and once you know F0, well, then you compute basically by recursion all the partition functions. And magically, they're all meromorphic because this guy is meromorphic. This wasn't quite so clear, for example, here in this form with the logs and dialogues. Yeah, and it seems like what we find here, the business of jumps, in a way, which is very similar to the story of this class sigma. The jumps are related to these BPS Riemann-Hilbert problems that like Tom has formulated. So for example, we can compute for this ratio of partition function shifted over partition function. What it gives is just the magnetic coordinate, or this should be BK, where the BKs are exactly the functions which represent part of the solution to the Riemann-Hilbert problem Tom has associated to the resolved conifold. So this is like also what, yeah, an analog of Kohai's identity relating a magnetic coordinate to a partition function. And here just what comes out is the part of Tom's Riemann-Hilbert problem. And what is also very suggestive is you can look at the jump functions as functions of slightly redefined variables. And with these variables, it really looks like these jump functions have all the properties to be identified with difference generating functions. And here what you recognize on the right-hand side after proper matching of parameters are exactly the jumps defining the Riemann-Hilbert problem of Tom's. So this is for the one magnetic coordinate and that is for the other one with the power to the k. Okay, so now I'm really at the end. So here in this case, for the sake of comparison, what one should keep in mind is we are in a case where one has no compact Four cycles. So in that case, you would and should expect that the tau functions and the partition functions just coincide. There's no difference between these two objects in that case. That is non-generic and is different in the case with compact Four cycles. And yeah, I would take these results from the resolved conifold as a first hint that in fact the picture that we have seen concerning relation topological string partition functions to tau functions, etc., may have a generalization beyond the class sigma, where sort of it is best understood at the moment. Okay, thanks for the patience and thanks for letting me go over time.
Okay, thank you very much. Any questions?
I would
please go
ask a
ahead.
question. Yeah, it's about this. Well, I wondered whether I could ask you to comment more on this relation that you attributed to Nekrasov, this kind of blow-up relation between the tau function and this generating function for the monodromy map. I mean, it seems quite surprising somehow. But I mean, is this an identity in terms of sort of formal expansions, or is it actually of analytic functions that this identity is given?
What Nekrasov has a proof for, to begin with, is that this particular combination of stuff formed out of, well, sigma eta and the generating function, what it certainly does is to satisfy this defining equation for the tau function, relating it to the Hamiltonian. Right? So,
okay.
I mean, this is, you see, it is basically an exercise in differentiation, right? So you're just having to, I mean, you just assume, well, everything is differentiable, and you just are careful about how dependencies are implicitly defined by the solution of this equation, et cetera, right? And then it's an exercise in differentiation to check that, well, he uses some property, some homogeneity property, which is satisfied in our case, which is satisfied in the Pauli-V6 case, of this Hamiltonian in terms of momenta and the mass parameters. But yeah, then it's just an exercise in differentiation, and you prove that the generating function satisfies this, well, this combination out of the generating function satisfies the equation that you would usually take to define the tau function.
Okay.
But of course, given this, then sort of the first step, I think, in the program to base sort of a alternative derivation of our claims on this observation would be, yeah, you turn it then into a definition, right? You didn't have an a priori way to fix the monodromy dependence yet, but this relation, of course, now gives you one.
Mm-hmm.
Well, then the next step would be, and I made some meager remarks in this direction, to see how this transforms when you change the coordinates on the character variety. Of course, it's obvious how the generating function will transform, just yeah, as usual. However, you have to take into account sort of these corrections or decorations in order to figure out how the tau function will transform. And what I believe, based on the observations that I told you about, is that this will exactly sort of amount to the change of ordinary generating function into the difference generating function.
Okay.
I mean, here's a lot to be done, no question about this. But I think what you see is very encouraging.
You make it sound rather easy, but I mean, physicists sort of, I'd always been under the impression that these two kinds of functions were very different. Like one was the NS limit and one was the unrefined limit, and therefore I should think of them as different functions. And now you seem to be telling me that up to some exercise in calculus, they're the same.
No, I mean, good. There was, I mean, in some sense, I was expecting a relation for a long time, but I somehow was missing exactly sort of these Nekrasov's observation. So, because I mean, well, in the study of some semi-classical Virasoro-conformal blocks, if you take those with extra degenerate fields such that you get all these apparent singularities, you can do that, right? You find indeed as the leading limit of Virasoro-conformal blocks, in fact, this generating function. And it's kind of, I mean, in some sense, both are defined through the monodromy map, essentially, right? Through Riemann-Hilbert. They contain the same information for sure. That is obvious, right? And furthermore, both somehow know about the Hamiltonians. They spit out after taking a derivative the Hamiltonian. But really what Nekrasov carefully worked out is really how exactly they do that. And that is not completely trivial indeed. So no, it's a nice calculation that he has. And so yeah, he made precise what the relation should be. I mean, there's an equivalent version, I believe, I mean, we're discussing this currently a little bit with Marco Bertola and Dima Korotkin, trying sort of to understand it better. They have a different take on that, which is probably equivalent, but I need more time sort of to really study all the details of their work and so on.
Okay, thank you. I should let Andrea ask your questions. Thanks.
Yeah, I was just wondering, there's a paper of Pasquetti and Schiappa from 12 years ago, something like this, where they consider non-perturbative partition functions from matrix models. And I think they consider the Chern-Simons matrix model, which is the large N dual of the Gromov-Witten theorem, the conifold. This is well, the closed example of Tobias' story. So I was just wondering if these partition functions that you find are different non-perturbative completions of what they consider. Like, I think they have some Laplace representation, Borel Laplace representation for the conifold free energy, but it's probably slightly different. I just wanted to know where the difference lies.
I must admit, maybe my collaborators, some of which I see here, can comment that I haven't had yet the time to, say, compare in detail. I believe sort of that these results on, say, Borel summation and the jumps are new. Of course, some aspects of, say, the Borel summability have been investigated in the literature. There is the one you mentioned. There is also more recent work of Marinho and collaborators. However, to the best of my knowledge, there hasn't been a closed form for the Borel sum and a study of the Stokes phenomena in closed form in the literature yet. That is my understanding.
Murat has raised his hand.
Yeah, so I can comment on this. So in particular, the one of Schiappa and Pasquetti. So as Joerg mentioned, so we're still working on this. But what seems to be going on, so there is two different representations of the Borel transform. And it seems that there's one representation. So you have to work out really the regimes of validity. There's one representation which in the resolved conifold language would be more appropriate for the t goes to 0 limit. And that's the one used in the paper of Schiappa and Pasquetti. And there essentially the resolved conifold looks like just an infinite sum of the deformed conifold with shifted arguments. So the argument is just shifted by integers and you sum over all of these. And there are similar structures which we had already used recently. However, the representation that Joerg presented is really a large volume one. So that is one where, so everything in the expression is in terms of Q coordinates. And there you can really read off the spectrum. So I think the main thing is that, yeah, so I think, so Boris also just mentioned to me in the chat. So there are other papers by Hatsuda and Okuyama who have considered some modified Borel transformation. But I think the picture is, they looked at a particular Borel transform. And I think now with this analytic expression of the Borel transform, we really can see that choosing the direction of the Laplace transform, that you have these jumps in the potential non-perturbative completion. And there is one distinguished one corresponding to the triple sign function, but then there are jumps as you move across the BPS state. So I think, as far as I know, so even all the papers that were mentioned, this was not explicitly appreciated in the literature before.
Amazing, that's super clear. Thank you.
Right, any other questions or comments? If not, let's thank Joerg again.
Thank you.
And I guess it's better to have 5 minutes break before the next talk. So let's move our schedule 5 minutes later. So we'll resume in 5 minutes at 2:20.
Hi, Kento.
Hello?
Hi.
Hi.
Yeah, should I try to
Yes,
share screen?
you're already a co-host, so you should be able to
I see. Okay.
share the screen or your tablet.
Right. Yeah. So what do you see?
Yeah, it looks great, and I can even see your cursor.
That's great. Okay, thanks.